Hi, everybody. It's a very exciting and challenging lecture today and also next week, the topic of quantum mechanics. Why are we discussing it in this lecture, in this class, in this course? Well, there are several reasons. The broad reason is that we are trying to extract some principles from the foundations of physics and neuroscience to reflect on high-level questions like free will and maybe consciousness and other questions that arise in the context of free will. So far, we discussed the tenets of classical physics. What is a physical state, the nature of time, causality, and so on and so forth. But the world, as you all know, is at the bottom quantum all the way through. Microscopic, macroscopic, everything is quantum. So the question is whether we have to revise, or to what extent we have to revise our conclusions so far according in light of quantum mechanics. And beyond that broader question, there are specific issues which are related to free will, which are connected to quantum mechanics. One major issue is determinism. Until now, the world was assumed in the physics theory that we discussed in classical physics as deterministic. So there were problems of predictability and chaos. There were issues of being interested in some coarse-grained variables and integrating out other variables. So this led to probabilities in statistical mechanics. In macroscopic systems, we're interested only in select degrees of freedom. But even in statistical mechanics and thermodynamics, an isolated system, if we are characterizing all the microscopic degrees of freedom, it is going to be fully deterministic. All right, quantum mechanics is potentially threatening this, as we'll see, as many of you already know. That's one issue, determinism versus indeterminism. Another, there are more subtle issues. For instance, the notion of locality, which is closely related to causality and to explanation in science, and to questions which will come to in the next part of the lecture, of the course. The nature of that is threatened by some theories of quantum, by some interpretations of quantum mechanics. According to them, for instance, there are coherent aspects of quantum mechanics over long ranges, spatial distances, that are incompatible with our local notion of causality, according to some views. There are exotic theories of quantum mechanics, which will not get to it, but anyway, just mentioned that in quantum mechanics, there's causal relations from the future to the past. Famous exotic theories of quantum mechanics. And then there are issues that, according to some interpretations of quantum mechanics, observations or observers, or the presence of observers, or even the presence of human observers, is crucial to the quantum mechanics, to the theory, to the framework, to the point that some would go to the extreme and say, without having consciousness, we cannot interpret quantum mechanics. Quantum mechanics requires not only observer, not only human observer, but conscious human observer. Okay. So for this or that reason, the issue of quantum mechanics figure in many of the philosophical discussion about free will, and in general about the mind-body relation. Okay, so what we have to do is to understand where these issues arose from and whether they are justified. And at the next lecture, the end of next lecture, next week, I hope I'll get to the more direct question, which is to what extent we expect to see quantum phenomena in the brain, in brain processes. I'll come to that at the end of the next lecture. All right. Many of you maybe studied quantum mechanics at some point. Those of you that didn't, I hope they studied it yesterday in the beautiful tutorial that Ariel gave. This is going to be technical, and not because there'll be many derivations, but because the formalism is so different from classical physics formalism. So those of you that are kind of threatened by bombardment of notations and formalisms, don't worry. What's important is, first of all, and most of all, is to understand the general thrust of things. I'm not expecting that in 1 or 2 lectures or 3 lectures you will be experts in quantum mechanics. You need to get the sense of it. Okay. Now, why I'm so excited and feel challenged in הנני אני ממעש נרעש ונפחד to lecture on this, because quantum mechanics is one of the areas in physics, in fundamental physics, that there is no consensus about its interpretation. It's an amazing story of chapter in the foundations of physics or science in general. On the one hand side, quantum mechanics is the most successful theory in the entire science. It is the predictions of quantum mechanics are obeyed by, and also quantum mechanics and the extension to quantum field theory, which we won't get to it. Anyway, it's to fabulous degree of accuracy. There is no single experimental fact that kind of violates quantum mechanics. I won't go to the cosmology, and that's gravity, that's a different issue, dark matter, dark energy, but that's gravity. But I'm talking about scales which are ordinary scales, or even, but anyway, so on the other hand side, as I said, there is no consensus of what it really means, interpretation of quantum mechanics, to the point that some of you may know the quote, famous quotes from Feynman: anybody that says he understands quantum mechanics doesn't know what he's talking about. And he advised his students or colleagues, shut up and calculate. Just be expert in how to calculate quantities in quantum mechanics, and then shut up. We don't really understand what's going on, so let's not worry about that. All right, I'm not happy with that. First of all, because no scientist should be happy with this state of matter, and secondly, because it will be hard, almost virtually impossible, to discuss the relation of quantum mechanics to the brain or to the mind or to the free will without being more precise about what it really means. Okay, good. So my lecture today, hopefully I'll get to it. I don't know, maybe not, then I'll finish next week. but is divided into two parts. The first part is more or less summarizing the conventional orthodox view of quantum mechanics, which is called Copenhagen School, the Copenhagen School of quantum mechanics. And I'll highlight its problems, why we're not happy with that. And then the next part of the lecture today, and perhaps it will go to next week to finish, is a theory of quantum mechanics, which is a small deviation and clarifying aspects relative to the orthodox Copenhagen school. But in my view, personal view, it kind of clarifies the theory. It makes it consistent. It makes it free of paradoxes, in my view. But on the other hand, it also clarifies what is bizarre in quantum mechanics. It's very bizarre. It's very bizarre, but consistent. No paradoxes. I'll come to it. It's not my own view, or my own theory, or my own interpretation, but it's one that I like very much. And I wish I would have been taught like this according to in school. Okay, most of you, I think, didn't get it in the right way when you learn, those of you that learn quantum mechanics at the university level. It's still taught in the wrong way. Okay, good. So let's start. Let's start with the basics. Okay, so we'll come back to Schrödinger's cat. Is it dead or alive? But we'll come back to it. Okay, so first of all, quantum mechanics defines differently what are the phase space of physical systems. It's not anymore momenta and coordinates like in classical physics. Until now, this was the phase space collection, the set of all possible, every point in a phase space was a set of coordinates and velocities or momenta. It's very different. It is a point, like shown here, a point in a Hilbert space. Hilbert space is a space where there are vectors, they are complex, the components of these vectors are complex. It can be finite dimension, it can be infinite dimension. We'll talk about finite dimension, just it's simpler. And it has several properties. One of them is that there is a norm and there is a scalar product. So I'll use the notation that physicists like, which is ket and bra. So a ket vector like psi is the state of the system, or wave function as it's known, is a column vector with components A1, A2, up to AN, n-dimensional if there are n degrees of freedom. And similarly, the bra vector is a row vector. And for each column vector, we can of course make the row vector fit, but it's common to make its complex conjugate the element. So A1 is a complex number, and A1 bar is the complex conjugate of A1. Okay. As I said, there is no, like psi will assume, and it is assumed in quantum mechanics, that all the states in this Hilbert space that are relevant are normalized. So they are all on kind of, it's complex, but anyway, think about it like a unit sphere. So psi dot psi is the scalar product of psi with itself, with ket and bra, and this is simply given by the sum over all absolute value squared components to be equal to 1. So one can say that in Hilbert space, a physical state or wave function is a ray, but you can say just a normalized. Okay. And similarly, you can take a dot product of two such states, or simply the sum of this product of the component wise, where one of them is is complex conjugate of AI, like written here. So in general, the dot product might be complex, right? But the norm, of course, it's okay. Anyway, good. So this is the phase space. So this is all the action is in this Hilbert space. We will extend it later on, but for now, this is it. All right. So what does it mean? What kind of physical attributes I can give to this state, to psi? Suppose you tell me psi is this and this, 1, 0.5 minus I, whatever. What kind of properties, physical properties, I can extract from that? So for this, we need to talk about observables. And in observables, in quantum mechanics, each observable, each physical quantity that can be in principle measured is associated with an operator. It's a linear operator. I can think about it as a matrix that take a vector and multiply on the right, but this matrix, but because it's infinite, it can be infinite dimensions, so we talk about operators, but you can think about it as square matrix, it's fine. And it's Hermitian. Hermitian means that A equals to, it's a complex conjugate. You may all remember that a Hermitian operator, a matrix, is characterized by a set of eigenvalues. They are necessarily real. So for an operator A, if it's Hermitian, there will be a set of, in n dimension, there will be a set of n eigenvalues AI that are necessarily real. Each one of them is coming with an eigenvector AI. I just use this notation. When AI is under these brackets, I mean the eigenvector associated with the eigenvalue AI. And these eigenvectors form an orthonormal basis. They are orthogonal and they are normalized. So it's an orthonormal basis. You can also write down this matrix or operator as a sum of a rank 1 a product of a column vector and a row vector, AI in this fashion here. Each one of this product is itself an operator, but it's a projection operator because it takes any arbitrary vector and project it onto the direction AI. And each one of them is multiplied by the eigenvalue AI. That's another formal way of writing this operator. And importantly, it's complete. It means that the basis AI, the set of eigenvectors AI span the entire space. And this can be written as taking the identity matrix and write it as sum over all these projections. So that's called completeness. So it means that every vector can be projected in this way. So if you take a vector and multiply it by this sum, you get basically the vector itself, right? Because it's just projected onto the basis like what I show here. So here, E1, E2, E3 will be, in this case, a particular basis. And that's kind of general basis. So that's important. So you have an observable if it is the coordinate of a particle, if it is the spin of the particle, if it's the momentum of the particle, the energy of the particle. Each one of these physical variable, there is a Hermitian operator in this Hilbert space which corresponds to it, and all the possible values that this observable can have are these eigenvalues. Nothing, if it's not part of the eigenvalues, that it cannot be observed. It's called quantization. Energy will take only one of the values that the eigenvalue of the energy of the Hamiltonian Hermitian operator, and so on and so forth. All right. So this is the observables, Hermitian operators, and now about dynamics. how such a state psi evolves in time. Okay. Okay, so the answer here is that the famous Schrödinger equation. So ddt, first order of a vector psi at a given time is given, the derivative is given by the Hamiltonian operator on psi. So Hamiltonian itself is a Hermitian operator, the energy operator, and it's you multiply it by psi. So this is kind of an equation, a matrix equation, and you can solve it. We assume H is independent of time. You can formally write the solution of that as e to the minus it times h. T is time, h is this Hermitian operator, so it's exponential of this Hermitian operator times some initial condition. It's a first order equation, so as usual, you need to specify the quantum state, the wave function at 0, and if you know that, you can compute the wave function at any time. All right. This is called unitary dynamics, but because H is Hermitian and it's e to the minus I times H is a unitary operator. It preserves norms, and all the eigenvalues of H are real. So this is like a phase, e to the minus I times a phase. All right, so it's a unitary matrix, and therefore it's a unitary dynamics, which makes sense because psi has to remain normalized. If you start with a normalized psi, it will remain normalized. All right, okay. In passing, this is still temporally micro-reversible. Interesting, although it's a first order equations in time, but all that happens when you put t to minus t is you reverse the phase instead of minus it to plus it, and as we'll see, all quantities will not be sensitive, all observable will not be sensitive to the change in phase. Okay, but that's not something that I'll focus on in this quantum mechanics. Okay, so now I said, so now we know psi, in principle, we can compute psi at all times, starting from initial condition. Now we have these observables. We know what are the for each observable, we know what are the possible outcomes of an experiment. It's A1, A2, A3. For instance, for the energy, it will be E1, E2, E3, where the E's are the eigenvalues of H, of the Hermitian operator. But which one of them will come out in a given experiment? So the answer is, it's not going to be deterministic. So the evolution in time of the wave function is deterministic, Schrödinger's equation, okay? But the outcome of an experiment that measures some physical properties is going to be not deterministic, it's probabilistic. So there is a possibility in principle, probability non-zero, that I'll get A1 if I measure A, or A2, or A3, and so on. And the rule is the famous Born rule, which says that if you have psi in given time, and you measure a particular observable, then the probability that you see AI is given by this absolute value square of the overlap or the dot product or the projection of psi on this particular eigenvector. Okay, so you can see that you can write psi in terms of all these vectors AI, this basis, and the coefficients squared are going to be the probabilities. Okay, so once I know psi of t and I know the basis, the projections of psi on each one of the eigenvectors, I can compute what will be the probability that I'll get AI as an outcome of an experiment at time t of A. Okay, until now, more or less, you're with me? Okay, good. So now things become complicated just because of Hilbert's, no physics, just the very fact that we said that states are vectors in Hilbert space and observables are these operators and so on, we get into trouble. And the trouble is we want to measure in a given state, we want to measure more than one quantity. Suppose I want to measure coordinate of a particle and the velocity of that particle at the same time. So there will be an A for the coordinate and there will be B for the velocity, or and so on and so forth. What's going on? What will be the case here? Okay, so now we have to, so here you have a set of AI and eigenvectors for A and a set of eigenvalues BI and corresponding eigenvectors for B. Both of them are Hermitian operators and they are legitimate and fine. You can express I as, you know, completeness in terms of A's, and you can express the identity I in terms of B. So each one of them is a kosher Hermitian operator and so on. But now there are two cases. One case is that A and B commute, which means that AB equals BA. In that case, you can show that you can generate a basis for the Hilbert space, which is each vector is a vector which is eigenvalue, joint eigenvalue of A and B. So they have a joint set of eigenvectors. So I write it like AIBJ. Okay, it's an eigenvector which is an eigenvector of B with value Bj and eigenvector of A with eigenvalue Aj. And there is a theorem that said that this is possible. And in that case, again, that everything's fine. I know what is the probability of having an outcome AI and a BI at the same time would just be, again, the projection of psi on this joint eigenvector. So everything is fine. However, if they don't commute, then there is no such a basis. You have to choose. Either you express psi, you use the basis A, you express psi, use the basis B. You cannot express psi in a basis which is jointly eigenvector of A and B. Because of that, just because of this kind of algebraic problem, formal problem, the conclusion is that there is no way to assign probability, any probability, to the outcome AIBJ. In other words, you cannot simultaneously measure these two quantities. Famously, you cannot simultaneously measure the position of the particle and the velocity, because you can show that these two are non-commuting. Okay. And I think Ariel talked to you about uncertainty principle. You know, if you don't want to measure them precisely, but with some standard deviation, but I won't go back. I'm not talking about really precise measurement and precise outcome. It's illegitimate. That's the heart of all the problems that we'll have, or most of them. Okay, so you have to choose which one you measure. All right, most of what I'll talk will take the simple example. The simple example is spin 1/2 particle, and again, Ariel gave you more than what I'll give you. I'll just remind you that a spin, a particle, many particles, spin 1/2 particle is characterized by a three-dimensional momentum or spin, angular momentum or spin intrinsic, and it has Sx, Sy, Z, three components. Each one of them in quantum mechanics, each one of them has values of either 1 or -1 times 1/2 h bar, which I forget. So let's just take two states, because again, because the Hermitian operator has only two eigenvalues, eigenvectors, and eigenvalues ±1. So Sx has eigenvalues ±1. In other words, if I measure the spin in x direction, I get either +1 times 1/2 h bar or -1. And similarly for Z and similarly for Sy. And there are Hermitian operators, which I didn't write. Ariel talked about these matrices. Okay, but I'm showing you just Sx and Sy. So the Hilbert space is two-dimension, and I can write the basis as one of them will be the spin Z plus, so the value +1 for the Sz, and I write it as 1, 0. Or in the y-axis, I write Z minus the other one, so 0, 1. So that's one possible pair of eigenstates, eigenvectors for SZ. I can also draw the eigenvectors of Sx, and there will be x plus, so just notation, the eigenvector Sx with +1, and it's 1, 1, and S minus, it's with 1 minus, it's 1 minus. This is why it's 45 degrees aligned. All right, is this clear? So these are just examples, a two-dimensional Hilbert space, but again, I can choose to characterize them by the basis SZ plus and SZ minus, or Z plus and Z minus, or X plus and X minus. There is also Y, but it has complex. That's enough for us, SX and SZ. All right, okay, two-dimensional Hilbert space, that's the simplest one and shows beautiful, almost all that you need to know about quantum mechanics in principle, not of course in practice. All right, questions up to here. Okay, I didn't show it, but I can tell you that these two, you can figure out from this diagram, but anyway, that these two operators or observables Sx and Sz are non-commuting. Okay, so it means you cannot measure simultaneously the momentum, this angular momentum, the spin at X direction and the spin at the Z direction. You cannot measure that. All right, so let's assume, I want to talk about measurement. So let's assume H is 0. If H is 0, then momentum is known to be conserved. Okay, so, and I want to do the following. I want to start with this wave function at 0, which is in the X plus direction, so just 1, 1. And I want to apply now the Born rule, and the Born rule says that you take this and project it on Z plus or on Z minus, square it, and you get the probability. So it's easy to see that this will be this will give equal probability to Sz plus and Sz minus. So if I want to measure when the system is at that state, I want to measure the spin in the Z direction, I can predict, I don't know what will be an answer. The quantum mechanics theory predicts that you will have 1/2 probability to get +1 or -1. If you repeat it many, many times, you'll get half of the times +1, half the time -1. It's not that we don't know. It is, we know that the probability will be 1/2 if you repeat it many, many times. The fraction will be 1/2, the frequency. Good. Now, suppose I do the measurement. Ariel, I think, told us a little bit about it, but how? But we'll do the measurements and it comes out to be +1, okay? So now I have a problem because now suppose I am doing the measurement again, right after the first measurement. I'm doing it again, I measure the spin at the Z direction. Well, it's not likely, well, it will be very bizarre if now I'll get -1. In other words, that there is no continuity in the world, that God created a world where one measurement after the another, right after that, and assume there is no interactions outside and something, just I measure the same spin twice and I'll get different result. So this doesn't make sense. So it must be the case, and it's against experience. So it must be the case that if I do the experiment again, right after the first one, I'll get again +1 with high probability, with almost probability 1. Okay? So what wave function am I after the experiment? Because if I am still in my original wave function, then I should get -1. I should get -1, 1 with probability 1/2, the Born rule. So I must conclude that after the first experiment, my state 0 plus, mean right after the time of the measurement, will be 1, 0, will be Z plus, because this is the only way to be consistent with the Born rule. Because if I am after the measurement in this state, Z plus, then of course, if I repeat if I now do the experiment, I'll get with probability 1, Z plus. Is the argument clear? Okay, just consistency and continuity, assuming that the world is not jumping all over the place. Now, is it a problem or not? So, is it a problem? Do we have a problem here? On one hand side, I claim, and this is a subtle point, I want you to listen carefully. On one hand side, I claim it's not a problem. Why? Suppose I have a smooth process, classical, okay? But it's random. Suppose I have random walk, okay? And I don't know, you know, I have some probability that it will be here, or it will be there, or it will be there, it will be all over the place, according to random walk statistics. But now if I, at a given time, measure the location of that random walk, I am pretty sure that if I measure it again very immediately after that, I will know for sure where it is, or very close in close neighborhood, right? Because it cannot jump immediately to another place. Is it a problem? Not at all, because we can call it in statistics conditional probability. So the probability that the spin z is +1 or -1 a priori is 1/2. But the probability conditioned on the fact that right now, I saw it to be +1 will be 1, that I'd see it 1. The conditional probability will be very different from the a priori probability if I've seen it. In other words, conditioned on the fact that I've seen it to be, take a coin. Before you toss it, you say 1/2, 1/2. After you toss it, you look at it, you say, well, you know, it's head, good. You know that if you look at it again, it would still be a head, right? So in other words, it's conditional probability, so you expect it to be so. Okay, is it clear? Why we have a problem, why it is difficult in quantum mechanics. And the reason is, then this is the subtlety that I want you to appreciate. The reason is the following. We started with psi that is pointing in the x direction, all right? In the SX direction. Now, until now, we spoke about the outcome of the measurement in the z direction. And I said, a priori, it's +1, it's 1/2 each way. After I made a measurement, conditioned that I saw it to be +1, it will be again +1 with probability 1, so that's fine. But what about measuring SX? What happens to this? So what can I say about that? So I know that before the measurement, if I would measure the spin in the x direction, it is 1 with probability 1 and 0 with probability -1, because this is eigenvector of Sx with eigenvalue +1. But after the measurement of the z direction, the psi is now 1, 0, is z plus. But z plus can be written as a superposition of x plus and x minus. So now the probability of Sx to be 1 is 1/2, and -1 is also 1/2. So what's going on? We completely lost all the knowledge about Sx. This is strange, right? Because if you'll do it in classical probability, there is absolutely no reason that measuring one quantity, measuring position in X, you will lose information about position Y. This is strange. After all, what is a measurement? Is observation, is looking at what happened. Why, if I look at my Z direction, SZ, I lose information about SX. I completely don't know what will happen now after measurement of SX. So this phenomena is called collapse of wave function. It was raised to the level of one of the axioms of quantum mechanics by John von Neumann, called the collapse hypothesis. And it basically says the following: we don't like it, but that's fact of life. In quantum mechanics, there are two types of dynamics. One dynamics is smooth dynamic, the Schrödinger equation. It's valid only in between measurements. However, in any measurement, the dynamics is discontinuous. It jumps from psi 0 in our case to psi 0 plus because there was a measurement at 0, and the wave function collapses to the eigenvector of the corresponding eigenvalue that was the outcome of the measurements that you just did. A collapse of the wave function. And again, I'm stressing, it's not simply that now I know what SZ is. It is the collapse means that now I lose all information about the other things, which, it's like in our case, SX now is completely random. If I'll do now measurements of SX, plus, minus. So how do we interpret it? So that's the, okay, so here's the summary of what's known as the quantum, Copenhagen interpretation of quantum mechanics. State space are wave function in a unit vector in Hilbert space. The dynamics is smooth in between measurements. Observables are emission operators, and the outcome of experiment is quantized because the results of the measurement can be only one of its eigenvalues AI. The outcomes are, the predicted outcomes are probabilistic, Born rule, given here. And then following a measurement, there is a collapse of wave function. After measurement A with outcome AI, this is going to be the wave function. Okay. That's the set of, if you want, axioms of traditional Oxford, not Oxford, orthodox, not Oxford, but Copenhagen, the standard textbook axioms of quantum mechanics. And then from this on, follow Feynman and calculate. Now, people are obviously we are not happy about that because, as already, I hope I convince you that to interpret this, it must mean that there is something strange about measurements in quantum mechanics. Because if the measurement is just a passive observation, it's impossible that this measurement will destroy knowledge about physical variables just because I looked at them, okay? So what's going on here? So now here, all hell breaks loose in terms of theories. Measurement and collapse. This is the measurement problem. There are books, there are conferences, there are papers, debates. What's going on about this? And obviously, in this interpretation, measurement is an active process. You measure, and by measuring the system, you destroy something about it. It's not simply passive observation. It's a fantastic, I don't know, philosophical, metaphysical story. It destroys information, as we saw, and it does not obey Schrödinger equation. Okay, what are the explanations? There are many. First of all, measurement devices are macroscopic. That's one line. And it started from the 20s, from the birth of quantum mechanics. Arguments, Niels Bohr and Einstein and Heisenberg and Schrödinger and everybody argued about. And one of the ideas was measurement is not part of quantum mechanics because you have your quantum spin, but it's interact with this big device, with this magnet or whatever. Quantum mechanics is not relevant to these macroscopic devices. Why? We don't know. Okay. Or maybe it is relevant, but the interaction is so complicated that it's not really collapse, but it's very almost collapse or whatever. Measurement is macroscopic. Other ones are saying more philosophical. No, quantum mechanics, in quantum mechanics, you cannot observe, you cannot measure a system without perturbing it. There is no way. And Niels Bohr and Einstein were going back and forth conferences about devising and counter-devising clever experiments that will measure something without perturbing it. And every time Einstein came up with such an example, Bohr came the day morning after and showed him, no, you're wrong. You do perturb the system. So, but anyway, that's one line of thought, okay? That the quantum system is so sensitive that any measurement, you have to send a photon, but the photon will knock out the electron or change, whatever, the spins. You cannot really make a measurement of a quantum system without perturbing it. It doesn't matter whether the measurement is quantum, the device itself is quantum classical. It's just always perturbing. Now, this is, by the way, right. But the question is whether this is the answer. In other words, suppose I take into account this interaction, what happened to the collapse? So it is true that measurement in a quantum system is likely to perturb it, okay? But it's not obvious that this is the reason for these weird things like collapse. Furthermore, if measurements is such a big perturbation, what do we learn from a measurement? It's not clear. We're supposed to observe the properties of the system, but instead we bang, destroy it. So it's not consistent. On one hand side, we rely on our measurement. On the other hand side, no, measurement is a big perturbation. So there's something inconsistent about this interpretation. And then there are more philosophical human observers and conscious observers. And so some people say, well, we don't understand consciousness. We don't understand quantum mechanics. So we'll put them together and one will solve the other. All right. Okay. There are two more aspects which I want to emphasize. One is, let's forget about the collapse and the measurement, the indeterminism. We said it's probabilistic, one of the axioms of quantum mechanics. And famously, Einstein didn't like it, never liked it. Does God play dice? Okay, he said God doesn't play dice. Well, the answer are vary. Some say yes. Too bad, God plays dice. The world, the quantum world, is indeterministic. And that's the view that I'll take. I think that's the most consistent and the simplest explanation of quantum theory. The others, as you might know, resisted that and said no. The reason why it's probabilistic is because it's somewhat like statistical mechanics, because there are hidden variables, hidden degrees of freedom that the quantum dynamics doesn't capture, and this is the origin of this so-called stochasticity. But if you will map all the hidden variables, every degree of freedom, it will be deterministic. Very, very well-known controversy. I don't think anybody came to a convincing story about that, and there are bad inequalities. I don't want to get into that. It's a fantastic part of science, of the foundation of physics. And then there are more, I would say, bizarre explanations. Very famous one is many worlds. It says, you know, it's not probabilistic, but every time you make a measurement and you get A1, it takes you to world A1, and the trajectory now will be one world. And at the same time, A2 will take you to another world. In other words, it's not really probabilistic, but it's really branching our world to many, many worlds. And each one of them is deterministic, but I don't want to elaborate on that. There are books and papers on that. I'm going to choose one. Okay, it's simplest. Okay, and the most consistent with the mathematics and experiment. No hidden variables, no many worlds. I don't know, there is no proof that we don't make many worlds, but it's very not parsimony. We have one world and the world is not deterministic. All right, then I want to point out to another aspect which is the same as before, but it has a different name. But it's related to what we discussed before about it's related to the collapse, but it is something to, to emphasize. This is called coherent superposition. When people talk about quantum system is superposition, linear superposition, what does it mean? So again, I want to emphasize the thing which I said before the collapse. So here's the example again. We have a wave function which is 1, 1, okay, this vector 1, 1 in the spin. So there are two ways to look at this wave function. One way is to say, well, it's a superposition of z plus and z minus, and therefore, according to the Born rule, it has probability of making of seeing a z plus or minus is 1/2. And then from that perspective, after the measurement, you say, okay, now I know that it is 1, so there is a change from this to this. And as I said, this by itself is okay, because it's sure, after I did the measurement, the next time, conditioned on the outcome of the measurement, I'm in a different state of knowledge. Good. However, the problem is that this story, this up till now, if I change plus to minus, or to I, or to any other relative phase, complex phase, with norm 1, like if I change plus here to minus, or to the I put there I, it will be the same story, right? Okay. However, this particular one with coefficient 1, 1, is at the same time also x plus. This is what you mean coherent superposition. It means that it's not simply a mix of two terms, z plus and z minus, but it's a mix of these two terms with a constant relative phase, in our case, plus 1. Because of that, it at the same time that it is a mix of z plus and z minus, it's also x plus here, okay? And then I have, as we said, prior probability to be 1, and then after the experiment to be plus minus 1 with probability 1/2. So when we talk about coherent superposition, we emphasize the fact that when we write the wave function in terms of a combination of eigenvectors, it's not simply a combination with amplitudes, absolute value squared, which given the relative probabilities, but it has a certain phase. If I choose here plus to minus, then this upper part will still be okay, but here it will be the opposite. It will be probability to be in the minus state 1 rather than in plus state 1. So this is the coherent superposition aspect. And this will end up with this famous Schrodinger's cat paradox, which you all know the story. You take a quantum particle, radioactive particle, that has some probability, has half-life time, a probability to emit radioactivity or not to emit radioactivity. If it emits radioactive particle, it breaks a cup in a cyanide glass, and then the cat will die. Otherwise, the cat will be alive. And you keep it there, the closed box, and then you observe it at some point. And now the question, you observe it, you either find the cat dead or you find the cat alive, which is fine. And let's say with half probability it's dead, that's all, everything is fine. But the question is, at what point the cat died? If you see it die, right? At what point the cat died? The problem is that until you observed it, according to the mathematics of the evolution, the smooth evolution of the state of the system, according to Schrödinger equation, if you prepared the particle, the quantum particle, in a superposition of deintegrating, or emitting a particle or not emitting, stable or not stable, you made it a superposition, then the cat itself together is also superposition of dead and alive. Okay, you open it, you see it dead. At what point it died? It died now when you observed it, when you collapse it, died before, but why before? I mean, before it was in a superposition state. That's the paradox, the famous paradox of Schrödinger equation. That's the problem of being a coherent superposition. So in other words, according to quantum mechanics, before the measurement, the cat was not in a state that we don't know. It either died or didn't die, but it was well-defined state. Either it was dead or it was not dead. No, it is in a coherent superposition state, like our wave function. It's not simply, I don't know whether it is a z plus or z minus. No, but it was at the same time also a Sx eigenvector. Okay, so that's the puzzle. This coherence. It's one of the big puzzles of quantum mechanics. What's going on? How can a cat be in a superposition state of being dead or alive? It doesn't make sense. And when I look at it, it decides to be dead now. When I looked at it, it doesn't make sense. So this is one of the beautiful puzzles or paradoxes of quantum mechanics. All right. Now, questions and comments, and then we will take a break, and then we will work out our way out of these problems. But other questions until now?
Could you repeat again, what was the problem with the view that maybe we just don't know the whole story of quantum mechanics, and the whole probability things are from some variables we didn't account into the theory?
Okay,
there might be an explanation that everything is deterministic.
Wait, if you show your face and we know who is speaking, it will be helpful.
Okay.
Okay, Daniel, what is the question?
The question was, you said that one idea to solve the problem that we have non-deterministic, are the hidden variables.
Yeah.
So what's why do you oppose the idea of the hidden variables? I mean, if you come from a deterministic, let's say, from Newton mechanics, that would be the most, or like until now, basically, and including thermodynamics, we didn't had anything which is just purely probabilistic.
There is, it's a whole story which I won't go into it, but there are famous Bell inequalities that predict that if there are no hidden variables, there will be certain inequalities obeyed or violated, and there are beautiful experiments that that violate these inequalities. There are empirical evidence that, with some caveats, that make the hidden variable story not plausible. But we don't have time to talk about that. But there is a very strong grounds to reject that. There are others which are I put it under hidden variables, but they're more subtle. Like, for instance, that instead of Schrödinger equations, you have the Schrödinger equation plus you have some nonlinear small term, maybe noisy, maybe not noisy, but this small nonlinearity acts like a noise. There are theories like that. I don't think anybody made sense of it, or there is any prediction that are consistent with that. Okay, more questions. It's not enough to say hidden variables. You have to say what physics they obey, and are they are obeying Schrödinger equation, they obey causality. This is where Bell inequalities come into play. They put restrictions on that. All right. Good. All right. Hafsaka. Let's take 10 minutes. Come back with a classical cup of coffee and continue. Okay, Shane, are you with us?
Hello.
Are you okay?
Yes.
Good. How is it?
Somehow I knew you were gonna call me after Shane.
Okay. All right. So let's start. I'm going to describe what's known. Sorry. Oh, here it is. Consistent quantum theory. I don't see Chiani. Why did she disappear? How's it? Can we see you? How's it? You can drink coffee or whatever. I don't want to talk to black square. It's not pleasant to talk to black squares. All right. Okay. It is, thank you, Chanu. It is called consistent quantum theory. Okay. It is a beautiful work, primarily by a physicist named Robert Griffith. He has a book already, I don't know, 10 or 15, I don't remember, years ago, maybe more even in the 90s. A book devoted to that. But in the last 20 years or 15 years, it became more and more popular, or it turned out that it is similar with some changes to other attempts to make sense of quantum mechanics, and things have some differences, but there's a commonality. I first learned about it from my old mentor and colleague, Professor Pierre Hornberg, physicist at Bell Labs, a fantastic human being. And when he retired, he decided to think about quantum mechanics, and he let me, he alerted me to this literature, because practicing physicists don't talk about it, don't worry about it. Computational scientists definitely don't talk about quantum mechanics. Anyway, I really indebted to him to show me the light. All right. Okay. So what it is all about, and there is a tremendous amount of literature on that by Griffith, by colleagues, and so on, and Ariel, some of which should be already maybe in the Moodle, some of it should be there. I really invite you to look at it. Okay, so what it is known, the basis is known, the single framework rule. It is going to be not very different from the axioms and the formulation, kind of orthodox formulation of quantum mechanics. There are not many rules, and there is no consciousness involved, and so on. And it's going to be indeterministic, probabilistic, axiomatically probabilistic. However, it sets the rule. And the rule is, there is something like framework, and I'll explain what frameworks are. But the basic pill that it will be hard to swallow is that a given system at any given time has more than one possible physical description. So in that sense, there is no universal, a single universal description of reality. Okay? The same system at the same time can be described physically, its physical content, by different frameworks, okay? And these frameworks are incompatible. So you cannot really compare. You cannot say, oh, in one framework, the properties are these. How come in another framework they are there? Or mixing between frameworks. You cannot compare two different frameworks, and you cannot combine. You cannot take a question or set of questions which have one from one framework, another from one. It basically makes order what types of questions are making sense in quantum mechanical system and what types are not. So that's the single framework rule. In other words, all the questions, description of reality, have to be within a single framework. Now you can say, well, let me consider another framework. Then you have a completely consistent and exhaustive reality description of the same system in another framework and so on. But you cannot say, but I got here and now I get there. Sorry. So this is, if you want, the metaphysical difficulty. Quantum mechanics doesn't have one unique description. Now, in classical systems, we also have somewhat like that. For instance, you can describe the system in coordinate, and then you can rotate the coordinates. And all kinds of transformations that you can do, rotation, translation, gauge transformations, and so on. But in all these cases, there are rules, simple rules, intelligible rules, how to connect one from another. So there is no contradiction, there are no paradoxes. You know how to take one and to relate it to the other coordinates, if you want. In quantum mechanics, there is no way. There is no way to take one physical description and to make it by some transformation consistent with another physical description. The two are separate and are incompatible. What you gain is that within one framework, everything is consistent in the sense that the logic is not quantum logic, it's the usual rules of logic. Probability is classical probability. There is no coherent superposition. All these weird things, they don't exist. It is simply probabilistic, as you will see. Okay? So the bizarre things in quantum mechanics, aside from the fact that there are multiple incompatible frameworks, is a mistake, is a logical mistake of mixing in incompatible descriptions of the reality of a given system. All right, so what does it mean? What's going on here? Okay, so the starting point is the notion of sample space. So how do we define probability or in classical systems, just probability? So we have a measurement or an experiment or some process, and the process can have multiple outcomes. And the starting point is what's known as sample space. In classical probability, definition of probability. You have a random process or random experiment, and you say it can have one of these two outcomes. And the set of outcomes, possible outcomes, is called sample space. So for instance, a coin toss had a set of two possible elements like head or tail. Or a dice, rolling a dice. The sample space is a set of 1, 2, 3, 6, and so on. Each one of this event in the each one of the element in this set of the sample space, each sample has assigned a probability, pi, and pi has to be bigger or equal to 0, and the sum of all these probabilities is 1, which means that the set of the sample space consists of mutually exclusive random events, right? It's either 1 or 2 or 5 or 6 and so on, and exhaustive. These are all the possible outcomes. This is why the sum of the probabilities is 1. And then there are more complex things like events. Events can be a composite. Like for instance, all the odd faces of the dice, 1, 3, 5 is one event. And now events are partially overlapping. They're not like the elements in the sample space, right? Obviously. And now the rule is that the probability of an event is the sum of the probability of each one of the elements of the samples in it. So that's the rule. That's basically what the logic of probability. There's some more of it. more or less that. Okay, good. So, which means one thing, we cannot just say we have a system and let's talk about probabilities. You have to define the outcomes, the possible outcomes that are mutually exclusive and exhaustive, and define probabilities of each one of these outcomes, and then you can define probabilities for the more composite events. Okay. So what are the sample space in quantum system? Well, the answer is, going back to our Hilbert space, the answer is that each Hermitian operator, each observable, defines a framework. Why? Because the samples, the set of samples is this AI, the possible outcomes of this experiment on A. And it's mutually exclusive because the states are orthogonal, and it's exhaustive because it's a basis for the entire state. And you have a probability for each one of these AI. So this defines a sample space. On top of which there are probabilities, and you can compute more complex quantities. So we'll call this framework, framework A. Framework AI means the framework defined by the sample space of the AIs of an observable A. You can have also framework BI, right? So the same thing, all the BIs and so on and so forth. Okay. The point is that if they are not commuting, as we discussed earlier, these two frameworks are incompatible. Okay. So a quantum description of a system, you have Hilbert space, you have a wave function. But for the same wave function, it's not enough. You cannot start to talk about probabilities. You have to say, I choose a framework. I choose a sample space. Then, once you have a sample space and you have your state, you can define probabilities. The usual rules of probabilities. Okay, that's going to be our rules. You cannot mix questions from one frame and another incompatible frame. It's not well defined. There is no such a sample space, because this cannot be a possible outcome of a single measurement, as we discussed before. You cannot simultaneously measure and B. It just clarifies. If you have non-commuting operators, each one defines a framework, a legitimate framework, but they're not compatible. So the same state in the Hilbert space will have two different, fully exhaustive possible description of its physical content, but they are not compatible. All right, so let's go back to our single spin one half, because this is enough. Okay, so let's suppose I have a state, a wave function given by this 1,1. So previously we said, well, 1,1 is, either combination, a linear superposition of Z plus and Z minus, but at the same time is also a state X plus. And that's what caused our problems, because when we did the measurement, we found a tension or contradiction between these two descriptions of psi. In one hand side, it's a linear combination of Z plus and Z minus, and so on. You measure Z. On the other hand side, at the same time, it's an eigenvector of Sx. So consistent quantum mechanics says no. The same psi, 1,1, has two possible ways to describe it, the physical content of it. One framework is the Z framework. In that case, psi is indeed a mix of Z plus and Z minus with probability 1/2. In that framework, the phase that is written there plus doesn't matter. You can write minus, you can write I. There's nothing about the phase, because it's just probabilities, classical probabilities. That's all. The phase is important because you can now switch to another framework, the framework of X. And the same side, the same vector in the Hilbert space is now in the other framework is the vector x plus. And it has probabilities 1 for x plus is 1 and probability 0 for x minus 1. These two descriptions are incompatible. You cannot say the same wave function is this and this. No. So a wave function in this context, a wave function is a pre-probability. It's a mathematical construct. It's not the reality, because this mathematical construct, wave function psi, has to be unpacked in terms of its physical description or content, depending on the different frameworks that you apply to it. So it is like Tamnun with multiple hands. Each hand is a possible framework. So the same vector, the same side, depending on which coordinate you use, which framework you use, will give you different physical content. So the wave function is not the story. Wave function is the potentiality of all possible all possible physical descriptions, depending on which framework you choose. Within a framework, there is nothing important in having their plus, because the only thing you can in a framework that you care about is the amplitude square, because it's probability. Okay, this is a very simple set of rules, and now, in order to unpack it more and talk about measurement, let me make it slightly more complicated. And this is where dynamics enters here. So until now, we said sample space, Hilbert space, okay? But when we talk about dynamics, we have to talk about trajectories. And trajectories, like in classical mechanics, you know, the dynamics is evolving trajectories. Also here, a trajectory, but a trajectory means really you have one Hilbert space, then you have the next Hilbert space and the next Hilbert space, and you have kind of trajectory connecting those multiple Hilbert spaces. Each Hilbert space describes the system at a given moment. That's kind of extension of the concept of trajectories. So that's called consistent histories. So it's easy to describe it in discrete times, because we are interested in outcomes of measurements at given times. So a trajectory, like I'm showing here, will be, let's talk about history. History is like a trajectory. So what does it mean? It means an observable or operator A1 with superscript 1 with a particular eigenvalue 1 at time t1, and another operator at time t2, or another operator at time t3, and so on. It's a collection of single time framework. Each one of these t is a framework, like z plus minus, and another time it will be x plus minus, and another time it will be y plus minus, and so on and so forth. So it's a collection of single time frameworks, a sequence of them, not collection, a sequence of them. Okay? But they are connected to Schrödinger dynamics. And Schrödinger dynamics is given here. It doesn't matter, but that's the way to write down on operator on Schrödinger dynamics. Okay. Now this is one trajectory. Now to go to the notion of sample space and make sense of probabilities, now you have probabilities on trajectories. So you take a family of these, like you know, z plus in time 1, x minus in time 2, y plus in times 3. This will be one trajectory, and then z minus and x plus and y minus will be another trajectory. You take a family of possible trajectories, and if they are consistent, you have a framework, but now extended in time. What does it mean consistent? It means that the trajectories have to be orthogonal to each other, and to span all, you know, the probabilities of all of them have to sum to 1. So the formalism is quite technical and complicated. There are beautiful correlations and consistency conditions. Beautiful mathematics to unpack it, but that's just give you the essence of it, and that's good enough for us. Okay. Why I'm going to this length, because I want now to describe a measurement. Okay, and to see how we rationalize about the measurement. So let's talk about the measurement. Okay, so now suppose I have my spin, okay, and I have also my device, the device. And I start from some initial state size 0 of the spin. And initially they're not interacting. So I just take outer product, you know, Hilbert space consistent of a spin state size 0 and a device state 0. What does it mean 0? Let's say I have some measurement device and there is some rest state. Before you measure, before it interacts with spin, there's some rest state, macroscopic rest state, quantum state of my device. So that's D0. So that's my starting. Okay, I want to put both the device and my spin in one isolated quantum mechanical state. Okay, so let's start with this. Size 0 can be Z plus, Z minus, whatever. And now let's see how things evolve in time. So because I'm assuming that my device measures spin at SZ, I'm going to make a measurement of the Z direction. So I know how it will evolve without the details. I'm assuming that my device will interact with my spin in such a way that Z0 plus D0 will evolve into Z1 plus and D1 plus. This is called D1 plus, it's called a pointer state. You have a pointer that says plus after the interaction with spin plus. And if the spin was minus, the pointer will be minus. It's called pointer state. So my device has many huge Hilbert space, but we're interested in 3 states, which are assumed to be orthogonal. A rest state, the needle is at 0, and then the pointer says +1 or -1. These 3 quantum orthogonal states. There are many others. We don't care about them. This is kind of quantum formulation of what the measurement is. There is between time 0, the 0 and 1 means time 0 and time 1. Between time 0 and time 1, there was some quantum interaction evolving in this Schrödinger equation, and we get this. Until now, everything is fine? Okay, good. So now let's see what's going on in our, what is going on in, how to describe it in terms of consistent histories and unpack the different probabilities. Okay, so one history on the left, top left, is a combination. So now all the histories are 2 times. So time 0, let's imagine that we start with a quantum state Z0 plus and D00. Okay, and then the histories that I take for time T1 is Z1 plus minus and D1 plus minus. So there are 4 possible elements in this sample space, right? Z1 plus, Z1 minus, D1 plus, D1 minus. So there are 4 histories here. Okay, you can show that it's consistent. And the probability, we know what the probability is according to the evolution in the temporal evolution, the Schrödinger equation here, that the probability of the history Z plus, Z0 plus, and Z1 plus, D1 plus is 1. And the probability of the other outcome, Z1 plus and D1 minus is 0. And the probability of Z0 plus and Z1 minus is also 0, because according to the evolution in time, Z0 plus, there is conservation of spin. So Z0 plus cannot turn into 0 minus. We started with plus, we have to remain in plus. So only 1 out of all these 4 histories has probability 1, the rest is probability 0. Okay, so
Hi.
yes.
Can I ask a question?
Yes.
Can you explain again, what does it mean, the spin of the device? What is D plus or D minus?
So I imagine I have a magnet and there is a clock on the magnet, you know, something that shows me. A spin goes into the magnet, it interacts, and then at time t1, the needle says +1. Okay, or it says -1. So it's basically reflecting some quantum state of my device, which collectively I call it +1. It just a pointer state. It just says some macroscopic state which correspond to what we will call a pointer showing, you know, pointing into +1, telling me that the spin was +1.
So of the
How
device.
do you do a measurement? You just what?
So the spin of the device means the spin of the measurement? So
The device is what is a measurement? There is some spin enters into a magnetic field and polarizes the magnetization of my device, and you know, and this is showing in some macroscopic ways and move the needle plus or minus. That's, you know, in your oscilloscope, you have a photon, you know, then you have spikes in the neuron, then you show some spike up plus and no spike 0. That's what you see in your device. Well, it doesn't matter if you see it, but that's what measurement is. The measurement device want to measure something. There are 3 possible, 4 possible, or 2 possible outcomes. The device must have different states because otherwise it will not discriminate between +1 and -1.
yeah. It's like the reading.
What?
It's like the reading that I can see.
Yeah, but whether you see it or not, it doesn't matter. The device is the reason why we're using it is because it has 2 different states corresponding to whether the spin that it was measuring was +1 or -1. Otherwise, it will not measure a spin, right?
Okay.
Now, even if I don't look at it, it will still be either in the plus state or in minus state, depending on what the spin was, right? So I'm not saying that it's important for me to observe it, but I'm just saying the reason why we use this measurement device, we build it, we design it, we engineer it in our workshop, such that when a spin interacts with it, it will, the measurement device will have a state corresponding to +1 or a state corresponding to -1, and 2 different states will be very different from each other. And then there is also an idle state 0. So these are 3 states that my measurement device must have, otherwise it will not be called the measurement device. Okay? This is the rationale here. That in between these 2 times, there is some interaction. I don't describe it, but it's quantum mechanical interaction. And again, I'm not using the fact that the device is macroscopic to say, well, it's strange. It's not strange. There is some complicated interaction and Schrödinger equation. But in such a way, the reason why I'm using this device to measure spins, because this device has a property that when the spin is plus, it will have a pointer state plus, and when it's spinning minus, it has pointer state minus. And I'm assuming that there is a conservation of spin. So during the interaction, I'm assuming the spin doesn't change its state. It's only changing the device state. Now, of course, the other devices will be more complicated, but I'm assuming a measurement such that the interaction between the spin and device affects the device state, but doesn't change the spin state. Okay, so if I start with plus, I put it into the device, then the device will tell me plus. If I started from minus, the device will tell me minus. Okay, so this is basically, I'm assuming that this is the outcome of the Schrödinger equation of this interaction, of this setup. If it wasn't, then this device is not a spin device, is not a spin measurement device, right? It doesn't tell me what the spin is. Spin's at. All right, it's a very simple kind of formulation what a measurement is in a quantum system. Okay, so now I can I can, let's look, I won't finish everything. I'll stop soon and we'll finish next week. But let's see several possibilities. One possibility is this history. So what is history? So I'm assuming history is now two Hilbert spaces, like sample space for time 0 before the interaction and sample space for time 1 after the interaction. So one possibility is to choose for the sample space at time 0, just one sample, one event, which is initial condition 0 plus, and the device in an idle state. And then for the next time, after the interaction, I have 4 possibilities, Z1 plus minus, D1 plus minus. One can show that this is consistent. But if you look at what are the probabilities of all these 4 histories, the probabilities are 0 for all 3 of them and 1 only for 1. Why they're 0? So for the one that I had here, Z0 plus going to Z1 plus, but D0 going to D minus, it cannot be because it's against the, it has 0 probability because it's against this dynamics, because we are assuming that the device, the quantum, due to the interaction, the quantum state of the device will point along the spin. So this, this state is 0, but also if you put Z1 minus, no matter what the device will tell us, this is also probability 0, because this will mean that the spin Z flipped its state due to the interaction from the initial plus to the second minus. And we assume, again, that the Schrödinger equation is such that it doesn't do that, that the spin itself doesn't change its state during the interaction. So it's a possibility, and we know what we can say. If we ask what, after the interaction, what was the spin of the particle? Well, the spin was plus. What is the probability that it has been minus? 0. What is the probability that it will be plus or minus if I do the measurement again right now? It's easy to see. It will remain plus. If it was plus, it will remain plus. If it was minus, it will remain minus. No collapse. Very simple. Okay. Now, here's a less trivial, maybe. I start like our story before. We start with 1, 1, with the x plus d0, and then the same sample space for t1. This is this one. It's another framework. It's another history, a set of histories, 2 times. Okay, but now the starting point is different. Well, here there are 2 histories which have probability non-zero. One of them that I start from plus and I go to minus, I go to plus, and then the device also goes to plus, and the other one that I go to minus and the device is minus, and this 1/2. And of course, the other 2 are 0 because there is no possibility that the spin will be 1 and the device will be minus, and vice versa. So this is another consistent framework, okay? In this framework here, in the second one, okay, as well as in the first one, in both cases, suppose I want to ask, okay, what is in time t1 after the measurement, what is the spin x of the particle? Well, too bad, because our sample space in both cases does not have this outcome. It all has about z and z1 or z plus or z minus. So this question is not a legitimate question in this framework, neither in the top framework nor in the bottom framework. In other words, we are not saying, well, the spin x was +1 in the initial time and then changed or can change its position to be -1 because of the interaction or because of collapse or because, no, it's just not a legitimate question to ask about the spin x at time t1 because it's not part of our sample space. You cannot talk about probabilities relative to a dice with 6 faces and ask what is the probability of the 7th phase. Too bad. It doesn't exist in your sample space. Okay? Here, and I'll end by this, here there is an inconsistent history. Starting with x0 plus and d0, as before, and ending with x1 to be plus minus and d1 to be plus minus. This is inconsistent. Why? Because the probability of all the elements, all the histories, all the probabilities are 0. Why they are 0? Because if we take the dynamics here and plug it into the dynamics for x0 and d0, it's easy to see that you will get a superposition of z1 d1 plus z1 plus and z1 minus d minus. In other words, the dynamics of the Schrödinger equation tells us that if you start from x0, from the spin x as the state, as the sample space that you are, as your basis, you are talking about Sx, then the final state at time t1 will be an entangled state where there is z1 d1, a mix of z1 d1 and z1 plus and z1 minus d minus. There is no state of d plus and d minus. So these states x1 and d1 are violating Schrödinger equation. So the probability is 0. So it's not consistent. So you see, that's kind of interesting. What's going on? What do you mean not consistent? It's not consistent because you are mixing in, so to speak, a state of a device which is polarized to +1 or -1, has well-defined states, either for z plus and z minus, and the spin z plus and z minus, but when they interact, if you start from x0, they form an entangled state. They form a state, quantum state, combined quantum state, which you cannot separate the spin and the device. So you never get x and d1 plus minus. You get a combination of z plus and d plus and z minus and d minus. So what does that mean? That means this is inconsistent history. This is not a legitimate a framework to describe what's going on in this system because it violates Schrödinger equation. Okay, so we'll continue next week from this point, but I want to give you already the flavor that there is no collapse beyond conditional probabilities because we never say that if we measure the spin z and get 1 or minus, then the spin x is this and that. We cannot say anything about spin x because we are using language of two frameworks which are incompatible. Okay, that's one thing. And the other thing is the following. So that's one outcome of this analysis. And the other outcome is the following. Depending depending what is the starting point, like here x0, okay, then we make a measurement. The measurement may make sense or may not make sense depending on the framework. So let me explain that. In the framework of Z1 and D1, the measurement makes sense because the outcome of that measurement would be spin up and pointer state up, spin down or spin down and pointer state down. But if the system is in an entangled state, then we look at the measurement device and we cannot interpret it. It's like a failed experiment. it's not that there is no, if I'm just looking at at this state here, at the final state, this combination entangled state here, okay? This entangled state is a state where this device is completely inappropriate for that. Because this device is designed to tell me plus, pointer state plus, I can interpret it, or pointer points down, I can interpret it, or idler can interpret it. There is no way to interpret in terms of a measurement outcome a state which is a combination of plus and minus. So you can see here, I think, the flavor of the theory, which is single frameworks. This is inconsistent framework because of the evolution in time. But even if you just think about this entangled state, you can see that it is a legitimate state. The entangled state, that's the single time, T1 state, is a legitimate quantum state, but it's not interesting one. Because the whole reason to make the measurement is because to get either plus or minus. This is the legitimate quantum state where the spin and the device are in this superposition, but I cannot even say that this state is a mix of Z1, D1 in terms of probability because it's not part of our language, of our framework. So I'll continue with that to next week to conclude this general framework about histories. And then I'll talk about two things, which will be most of the lecture next week. One is how do we go from microscopic to macroscopic? And that's extremely important because most of what we look at the brain relative to quantum mechanics is macroscopic. And that will lead me to the question, to what extent quantum phenomena are relevant to the brain? By which I mean whether the dynamics of neural activity in the brain is really affected by quantum phenomena. Okay? Questions so far? You're all overwhelmed or underwhelmed or? Am I the only one that is excited about that?
I'll see what the answer will be.
Of course, but I'm not talking about the brain. I'm just saying it's mind-boggling that there is no unique reality, right? It's somewhat like the many world, but it's not. We're not talking about multiple universes, but we're talking about the fact that all of a sudden reality doesn't have one answer. I don't know. To me, it's the only way to make sense, in my view, of quantum mechanics is to pay this price: probabilities and incompatible descriptions. Those of you that know about the variety of paradoxes, you appreciate that. Okay, so for instance, the Schrödinger cat is kind of the same story, right? That either you describe it in terms of entangled state, then you cannot say anything about the system, about the cat. You cannot call it a cat even. Or you want to ask dead or alive, then you use a framework where dead or alive are state, like pointer states. Then everything is probabilistic and there is no superposition. So anyway, okay, we'll talk more about it next week. Okay.
Thanks.
אריאל, רצית להגיד משהו?
Just I mean, here in the last line you have here, compared to the first line with the z, so you have the x0 and the x1 and the z0 and the z1. So the first line and the one before the last line.
This one and this one?
This one and the one on the bottom.
This,
And
this one?
the inconsistent history.
Yeah.
What's the difference between them? And this is x and this is z, but what's the but
because here in the time t1 there is x1, and here is
also,
x1.
But x1 from x0, and on the top there was z1 from z0.
No. But there is no, if you start from x0, there are no states like x1 and d1.
Okay.
X0 evolves into this entangled state.
But Z0 would evolve to the entangled state of X0 and X1, X plus and X minus.
That's the point. You use a framework, you have to decide which framework you use.
I see. That's the
framework. In the framework where you start from X0, it's not.
It's the same framework as above, just here it's inconsistent. Okay.
So like the device here would give us the spin only of the Z framework?
Can you say it again? In the bottom, you are assuming a state where you have x1 and d1 as a state, as a product state. x1, well-defined spin x1 times well-defined position of the pointer at +1. This state is not a legitimate state. It violates Schrödinger equation.
Because we are in the Z framework?
No, because the Schrödinger equation will tell you that D1 plus must come with Z1 plus, and D1 minus comes with Z1 minus.
So this is like a device for Z spin.
There is a state Z1 D1 plus, and there is a state Z1 minus D1 minus. There is no state, you cannot evolve into a state where X1 and D1. Because we assume that the interaction is such that it will not give you neither of these states.
But you started from Z0.
What?
But you started there from Z0.
Where?
And the one before the.
But now you can take X0 and write it as a linear combination of Z1 and Z2, and then come up with this outcome. You write X0, D0, let's say X0 plus. You write it as one of, Z1, Z0 plus Z0 minus. Schrödinger equation is linear, right? So if you combine these two, you'll get X0, D0, right? Let's say X0 plus. You take this plus this. This will be X0 plus D0, right? That's fine. But then, because of the linearity of Schrödinger equation, the outcome will be this plus this. And if you have minus here, the outcome will be this minus this. So the outcome here will be this. These two quantum states. Neither of them is this.
Right, but what in the previous
here?
No, in the previous Shekef, what made why don't we have the same rule with X0, D0? I mean, how do we get
X0 here?
Yeah.
Well, for a device, I mean,
so it's dependent
this
device.
This is a rule assuming the device measures spin Z.
I see. Okay. So
this is the device that measures spin in the Z direction.
Yeah, okay. So it's
of course, if I had the device in the X direction, the whole thing will, I'm assuming that the device, okay, I'm sorry that I should have said it explicitly. I'm assuming the device is a device that measures spin and the z direction.
Okay.
So you can't get any answer when you record X at some given time.
So I cannot have an answer like spin and after the interaction of the particle and the device, a spin x in the plus and a device in the minus or in the plus. This combination, none of these combinations are consistent with the dynamics that we assume for the system, which is different from here, because here, you know, I start from x plus d0, I get this state, I get to this state, but this state is now unpacked into these components, which is fine. These components are part of my sample space. Okay, and then I can give, I can write down the probabilities. So in both cases, I get this in terms of the Schrödinger equation. But what is the physical content of this, I have to take this bottom here and to relate it to a framework. This is a legitimate framework, and I can say, because it's a, you know, has 1/2 probability component here, 1/2 here, then the probability is 1/2, which is fine. That's what we described at the beginning, right? You have spin at x direction, you put it through this magnet, the Stern-Gerlach experiment, in the z direction, and probability 1/2 you get 1 plus, and probability 1 minus. But you cannot pass it through a Stern-Gerlach and say, what is the probability that the spin, that the device will be in the plus direction, and at the same time the spin will be in the minus the x direction? This combination are not allowed. So you cannot unpack this type of states into this framework. Okay, so this is why in this experiment you cannot ask about the x direction. Okay, at 1 after the interaction. Okay, very good. Okay, see you next week. Chanukah Sameach.
חנוכה שמח.
חנוכה שמח לכולם.